Hello everybody, my name is Arnaud Schoentgen and today I will present you a work done in collaboration with Jonas Zehnder, Pierre Poulin, Bernhard Thomaszewski, Philippe Meseure and Emmanuelle Darles. This work is about incompressible smoke simulation up resolution. But before talking about the method, let's first consider why we need up resolution. We can start by saying that nowadays we have access to fairly good tools to generate convincing smoke animations. However, very fine grids are usually required to generate the more detailed smoke simulations, making each simulation time step computationally expensive. Unfortunately, these long computational times can hamper artistic creativity when designing an art-directed smoke animation. In fact, an artist can directly control the simulation at its final high resolution, adjusting control parameters during an iterative process depending on intermediate visual feedbacks he observes. As we just mentioned, such an approach is not acceptable since each iteration of the design process might take sufficiently long time to hamper artistic creativity. In order to tackle this problem, an artist may want instead to control a lower resolution simulation before performing a final resimulation at the desired high resolution when the right set of control parameters is found. In such a scenario, each iteration of the detailing process is much faster to compute. In this example, we generate two different simulations using the same initial condition, but with different grid resolution. As you can see, increasing the resolution produces different smoke behaviors, leading to unpredictable simulation when going from low to high resolution. Therefore, such a naive approach also does not work, since the final high-resolution simulation is not predictable. Today we present a simple yet robust up-resolution method allowing an artist to resimulate at a higher resolution a potentially art-directed low-resolution smoke simulation. In this example, our method generates a high-resolution simulation very similar to the low-resolution guide simulation on the left. Note the differences with the high-resolution free simulation on the right, generated using the same initial conditions. Several methods generating a high-resolution version of a low-resolution physically-based simulation have been proposed in the past in different application domains. Bergou and colleagues introduced tracking method for simulated thin shells. Nielsen and colleagues erode a low-resolution liquid before resimulating a high-resolution liquid within a layer surrounding the guide. Some methods are focused specifically on smoke up resolution. Kim and colleagues use a procedural function to generate turbulences on low-resolution smoke. The turbulences are divergence-free and located in a spectral band, preserving the low-resolution structure of the smoke. This method is simple and elegant, but the generated simulations are not always plausible because of the procedural nature of the details added. A few methods use deep learning to synthesize a high-resolution smoke simulation from pre-computed data. These techniques require a large quantity of data and long computation time to perform training. Moreover, the resulting simulation depends on the dataset used to perform the training, which can be an issue if a user wants to manipulate simulation parameters. Another category of method apply empirical forces to reduce an error term computed at each simulation frame. These methods are usually inexpensive, but they lead to a non-optimal control and may generate oscillatory behaviors around a target state. The introduced forces usually also depend on parameters that need to be tweaked depending on the fluid properties as well as the scene configuration. Nielsen and colleagues constrain the low-frequency component of the velocity field to make it as close as possible to the velocity field of the low-resolution guide. In practice, density variation can be observed. This is mainly due to the fact that density diffusion and density dissipation depend on the resolution of the simulation. Similarly, Gregson and colleagues track tomography data. Their method does not focus on density matching and thus fails to reproduce the density distribution of the input data. Smoke density being what we observe, faithfully reproducing it when performing up resolution is crucial in order to generate a predictable high-resolution smoke simulation. Our tracking solution is very much inspired by optimal control method. This method controls a smoke simulation to make it match a small set of keyframes. They usually cast the fluid control problem into a space-time optimization problem constrained by the Navier-Stokes equations. Before introducing our up-resolution strategy, let's first consider the fairly standard fluid simulation algorithm originally introduced by Stam. Stam's method uses a MAC grid in which values for pressure and for density are stored at the center of each cell, and velocity components are stored at the borders. At the beginning of each simulation time step, smoke density is emitted in region covered by an active emitter. The velocity field is then modified according to the forces acting on the system. It is then projected in order to remove its divergence component. This projection step allows us to ensure conservation of mass in the scene. The density is then advected through our now divergence-free velocity field using semi-Lagrangian advection scheme. To do so, and for each cell, we consider an imaginary particle at the center of a cell that is advected in the opposite direction of the velocity locally estimated at its position. The density value interpolated at the backtrace position becomes the new density value in the cell. The advected state of the entire grid is computed by repeating this procedure for each cell. This sequence is executed at each time step to generate the smoke animation. In order to guide a fluid to match a low-resolution guide, we propose to modify the projection step of Stam's algorithm to include a tracking part. In particular, we want to modify the velocity field Vt using a vector field x in order for the high-resolution density distribution to be as close as possible to the low-resolution density distribution once advected through it. We define an error, ρr, corresponding to the difference between the current density at time t, advected by the current velocity field modified by x, and the density grid of the guide at time t+1. It is important to note that the density grid of the guide is coarser than the density grid of the high-resolution simulation. This implies that the quantity of information contained in the guide is not sufficient to completely determine what the high-resolution density distribution should be. Using an argument based on frequency, we can consider that the guide tells us what the low-frequency component of the final density distribution should be. To only track the low-frequency component, we therefore apply a low-pass filter B on the density distribution before measuring the difference between the distribution of the guide and the track density. In practice, we use a Gaussian blur. We can now develop an objective function that will be minimized using gradient-based optimization. We define a function phi by summing up the L2 norm of the previously defined error multiplied by a factor km. The gradient of phi m needed to perform numerical optimization is given by the following expression. As you can see, these terms depend on the following derivative, which correspond to the variation of the density after advection depending on each component of x. In order to compute this derivative, we must have a C1 continuous advection scheme according to the velocity field, which is not the case for an advection scheme using a bilinear spatial interpolation of densities. To make this operator locally C1 continuous, we use a first-order advection scheme with spatial interpolation of the density based on Hermite curves. It allows us to calculate an analytical expression of the advected density as well as its gradient. The use of a non-zero vector field x moves the simulation away from an uncontrolled plausible simulation. We therefore foster solution using a minimal velocity field perturbation. To do so, we add a regularization term to our objective function, with the corresponding gradient trivially given by this expression. Minimizing these two terms can, however, lead to a highly spatially varying solution. In order to calculate a smooth vector field, we add a smoothing term to our objective function to reduce artificial velocity changes. In practice, this term corresponds to the L2 norm of the gradient of the vector field x, with the gradient given by this term. Note that Km, Kr, and Kg are weights applied respectively to each term of our objective function. In practice, we always use the same set of weights to generate our examples. This set of weights has been experimentally found and corresponds to a good trade-off between realism of the simulation and accuracy of the density tracking. We always want to advect a density distribution through a divergence-free velocity field. Therefore, we have to remove the divergence component of our velocity field. In practice, we minimize our objective function for a general vector field that has non-zero divergence. During the optimization and at each iteration, we then remove the divergence of the vector field before using it to modify the velocity field of the simulation in order to advect the density through a divergence-free velocity field. Since our optimization problem is unconstrained, we can use the standard LBFGS algorithm to perform the numerical optimization. The use of a quasi-Newton method frees us from the computation of the Hessian matrix of our objective, which would be complex and costly in our case. We tested our method on various scenarios, from which we present here a number of examples. Let's first consider the case of a simple 3D plume of smoke. In this example, we generated a low-resolution guide simulation in a grid of 32 by 48 by 32 on the left. We generated a high-resolution simulation in a grid 4 times finer, tracking the guide. As a comparison, we generated a high-resolution free simulation without any control applied to it. Our method produces a simulation visually close to the guide, but enhanced with high-frequency details. We compared our method with Scheme, which uses a procedural noise function to produce a higher resolution version of a guide simulation. As a comparison, our method produces an animation visually closer to the guide. We also did a comparison with Nielsen, which constrained the low-frequency component of the velocity field to be as close as possible to the velocity field of the guide simulation. Although differences are more subtle, a better density matching can be observed in the simulation generated using our method. Lighting the previous animated density distribution using Spotlight gives us another look of the density variation in 2D, helping us to better appreciate them. We also quantify the root mean square error between each high-resolution simulation and its guide. With the set of parameters used to generate our results, our simulation produces, on average, a root mean square error 2 times smaller than with the method of Nielsen. Our method can also be used to track a low-resolution smoke simulation interacting with an object. In this example, we're guiding a high-resolution smoke simulation using a low-resolution simulation in which a plume of smoke collides with a 3D sphere. Note that although the sphere is not part of the scene in the high-resolution simulation that we generated using our method, we can faithfully reproduce the behavior of the smoke avoiding the absent sphere only by tracking the low-resolution guide. The sharpness quality of the tracking at the boundary of a solid depends on one term in our objective function among the 3 terms we are minimizing. In many cases, the method as presented does not reproduce the exact behavior of the guide at the boundary of a solid. We give the possibility to the user to explicitly take into account solid boundaries during the optimization of the velocity field. And of course, nothing prevents us from using our method with the low-resolution smoke interacting with an animated mesh. We also applied our method to track real-world capture data. Since we did not have access to tomography capture equipment, we used the public database from Eckert and colleagues. On the left, we show the data from Eckert and colleagues representing real-world capture data. To fit our optimization process into memory, we generated a guide from the data by applying a low-pass filter on it in order to handle an up-resolution factor of ×4 in reasonable computation times. The simulation generated using our method is displayed on the right. Note that the simulation faithfully reproduces the low-resolution guide in the middle while giving birth to plausible high-frequency details. Finally, we applied our method on non-physically plausible guides. In this first example, 2 simulations, A and B, have been simulated separately. By simply summing up at each cell the density of these 2 simulations, we can generate a new animation that is used as a guide. We generated a high-resolution simulation using our method, taking the previously defined simulation as a guide. The resulting animation is plausible, even though the guide is not physically correct. This example suggests the possibility of generating plausible high-resolution simulation by tracking compositions of low-resolution simulation other artists could want to do, just like compositing images in Photoshop. In this last scenario, a distortion has been applied to a rising plume simulation. The distortion allows us to quickly generate a low-resolution simulation in which the smoke rises in the air, forming here a spiral. Used in combination with this guide, our method allows us to generate a plausible smoke simulation following the behavior of the guide but enhanced with high-frequency details not affected by the underlying geometric transformation that has been applied to the low-resolution simulation. Here are statistics related to the example presented here and in our paper. In all examples, the up-resolution factor is 4. Due to the optimization performed over more than 40 million parameters in the largest example, the use of our tracking method remains computationally expensive. Indeed, the generation of a high-resolution simulation took between 36.7 and 99.4 times longer than the corresponding free simulation. Although important, we find this calculation time acceptable since the up-resolution process does not require any intervention from the artist and should be executed only once at the end of the edition process. Rerunning high-resolution simulation could certainly require more computation time as well as generate more frustration from an artist. During this talk, we presented a simple yet robust up-resolution method for smoke simulation. Our method allows us to generate a high-resolution simulation visually close to the low-resolution guide in terms of density distribution, but enhanced with high-frequency details. Our technique has been tested on several scenarios, and we believe that our method has the potential to shorten the creative process of hard-durated smoke simulation when used in combination with smoke control tools. Our method is currently based on an optimization process that unfortunately requires a long computation time. More efficient ways to perform the solve could be investigated. Although we focused on tracking of smoke described using an earlier formalism, extension of this method to liquid or Lagrangian system would be particularly relevant and could represent another very exciting direction for research. Thank you for your attention. Do not hesitate if you have any questions.